All right, so let's continue. So last week we were reviewing this model and data framework, and we still have a last part, right? So probabilities. So let's review probabilities. I think every one of you have learned probability and statistics. So here, let's just have a brief recap of the concepts that are most relevant to our course. Okay, so first of all, what is a probability? Okay, so the probability is a concept that describes the chance, right, of a random variable, not random variable, random event happening, right? It has many senses. For example, in the empirical sense, you would say it's the relative frequency of something happening. So maybe in the history, when people chose the natural language processing class, right? You find that out of 10 runs, 9, I did not have a final exam. So you would say, all right, so the NLP class has a probability of 0.9 of not having a final exam, right? Or it has a more philosophical sense, which describes the inherent characteristics of a random event, right? So you will say, okay, out of the universe in the natural language processing class, Yue Zhang teaches, okay, and there's 0.9 chance, okay, not having a final exam, all right? So anyway, so probabilities help us to get a sense of how likely something will happen, right? And random events are sort of described by random variables, right? We have variables to describe those events, and those variables will take values. Let's take coin tossing, for example, right? So if you toss a coin, it can end up with a head or tail, faces up or down, right? So you have a probability of the coin facing up or probability of a coin facing down. So the random event is tossing a coin. Its values, right, describe the outcomes, up or down, right? So the probabilities describe these outcomes. So if you cast a casino dice, you know there are 6 faces, right? You can have 6 numbers, 1 to 6. So the event corresponds to the random variable. You can define a random variable E, and it has different values that correspond to different outcomes, right? Normally, you give each outcome a probability, right? The probability of facing up is 0.6, right? The probability of facing down is 0.4. But if random event has many outcomes, the probability of each outcome will sum up to 1, right? So take either this outcome or that outcome. So if I describe each possible outcome in the variable r, okay, in the value r, then the sum of all possible r, PR, will be equal to 1. All right. So I just mentioned tossing a coin and casting a dice. But if you say, if I randomly say a word, okay, just close your eyes and think about a word, and you say that word, it's also a random event, right? And how many outcomes are there? So depends on your vocabulary, right? So vocabulary is the set of words someone knows or some model knows, right? So you will just randomly think about a word. Okay, so drawing a word randomly is also a random variable, right? So each word is a value. Everyone knows it. All right. So as I mentioned, so we're looking at all those random events that have discrete values to have an exam or not to have, faces up or down, or the number of the dice or a word. So every possible outcome has a probability. So if I draw these probabilities all together, it will be a like bar chart, right? So this bar chart describes how you distribute a total probability mass of 1 into all different possible outcomes, right? So this is a distribution. Some values of the random variable will have higher probabilities, while other values will have lower probabilities, but it forms a shape, right? A distribution. And in your probability class, if the random variable has two values, then it's a Bernoulli distribution. This is probably the first distribution you learned, right? If it has more than two values, then it's sort of a multi-Nulli distribution or a categorical distribution, as I show you here, right? If you have questions, you can interrupt. Well, there are more complicated distributions. So if you toss a coin multiple times, n times, right? Then you will have different outcomes, a combination of these heads up or down, right? If you toss it n times, there's k times you see heads. Then what's the probability of seeing k heads out of n tosses? So this is called a binomial distribution, right? So basically, you have this equation. Okay, I don't have time to go to many details, but you see, this is like k times, right? It faces up, m minus k times it faces down. And this is how many cases out of n tosses, right? You have k faces up. So this is a combination, right? So this first coefficient describes the combination. Right? Okay. So similarly, you will have a multinomial distribution describing like n different categorical distributions, the composition of n categorical distributions, right? So if I cast a dice n times, right? How many times will I have the number 1, right, in total, right? So this describes the combination, right? So not as simple as how many times I see 1, but say how many times I see 1, 2, 3, 4, 5, 6 in this number composition. Right? All right, but those are discrete random variables, right? And that's pretty much what you will see in all of the lectures. But if you read the book, you read, say, the chapter about a Bayesian network. If you read the book about random variables, you will also see some continuous variable descriptions. Here, let's just very briefly review them. So if a random variable is continuous, what does it mean? It means that the random variable can take any value in a range, right? So it can be a floating point number, real number. So it doesn't quite make sense to say what's the probability of my continuous random variable having the value 1, because it's only a small point, okay? You learned calculus, right? The chance of some continuous random variable falling into a specific point is 0. It tends to 0, right? So then how do we measure the probability? We can describe the probability of a continuous random variable using a probability density function, PDF, right? So it tells you, okay, how it distributes in this range. So, and then to calculate the probability, you will say, all right, so this random variable, what's the probability of it falling within a particular range, between 0 and 0.1, right? And then you can do an integration of this density function to know the probability of the variable falling into a range. Okay, not a point. A point probability tends to 0, right? And for continuous random variables, 2 of them you better know. So one is a uniform random variable, so the probability density is constant, right? Okay, so the larger the range, the more probable it is, right? So it grows linearly. So the other is called a normal distribution or Gaussian distribution. So it's sort of a bell shape, okay? It has a central point. So it's most probable, right? If it's distributed around this central point, okay? And when it goes to like a random vector of multiple dimensions, you like extend the density function into multi-dimensions, into a higher dimension space, right? So if I have 2 random variables, right? as a vector of 2 dimensions, then you know that it can have a like value of 0, 1, right? 1, 0 or 1, 1. So if it's a uniform distribution, it's like a plane in this shape. And if it's a Gaussian distribution, then it's like this bell-shaped stuff. Okay, so that's a quick review. All right, but then we care about multiple random variables. You know, if I do 2 things together, then they could be correlated or not. Okay, if you study hard, well, you're likely to get a good result in your exam. So these 2 random variables are correlated, or they might not be correlated. I can toss a coin and cast a dice, 2 random events, right? But whatever I do, if I have 2 random events, I have a joint event, joint probability distribution. What are the instances? As I mentioned to you, I can toss a coin and cast a dice, but you can also take a look at different words in a sentence, right? So the first word, second word, and third word in a sentence, there are 3 random events, right? So when you think about a sentence, the first word has a distribution. The second word also has a distribution. Okay, but if they are in the same sentence, of course, they are correlated. Right? They're not quite sort of independent of each other. And if you look at a sequence of part of speech tags, okay, they're also correlated. So each part of speech tag can take 1 out of like 34 possible values, say, but if they're in the same sentence, then they're correlated. The previous word is a determiner, then the next word is more likely to be a noun, right? So joint events. So when you have 2 random variables and they are correlated, of course you can measure the probability in a conditional form. So say, if I know that Yuan Shi studies hard, then I know the probability of Yuan Shi getting 95, say, okay? If I don't know Yuan Shi studying hard, okay, then maybe the probability distribution changes, okay? So how do I describe this? So I can use something called a Venn diagram. So I think everyone knows it, right? So this whole box is describes all possible events, you know. And this A describes an event, certain event A happening. This B decides, okay, this B happens, right? So and then if you calculate the probability of A, then what you do? You normally use this area divided by the whole area, right? every possible event happening, right? But if you describe, okay, the conditional probability of A happening given that B happens, then what do you do? Well, if you know B happens, then everything you count is within this circle, you know. You have to only calculate things within the combination where B happens, right? So when B happens, A also happens is this joint area, right? So you use this joint area divided by this circle to get the probability of A conditioned on B. It depends on what is your condition, right? So you calculate the ratio of A happening against the whole possible events, right? As I mentioned earlier, so this shaded area is when both A and B happens. So it's called a joint event. Okay, so the probability of both A and B happening is this shaded area divided by the whole area. Okay, so this is about joint event and condition probability. All right, I just went through quite quickly. All right, so conditional probabilities are described in this way. So say, given that my coin faces up, okay, what's the probability of the dice having a number 5? Or given that the previous word is hello, what's the probability of second word? So these are conditional probabilities. You describe them in this way. You can have multiple events in the condition. So given that the first, second, and fourth part of speech tag are a plural noun, a verb, and a noun, what's the probability of the third, right, part of speech being an adverb. Okay, so these are conditional probabilities. And you can, as I mentioned earlier, you could, right, also draw these conditional probabilities in the Venn diagram. All right. So what is conditional independence? Conditional independence says, okay, given B, the probability of A is equal to the probability of A itself. Okay, so it means that the ratio of the shaded area, okay, against the area of B is the same as the ratio between the area A against the whole area. Right. So this is conditional independence. And by looking at the equation, you know that conditional independence is symmetric. Right? If A is independent of B, then B is independent of A. Right? The two random events are not correlated with each other. And from the Venn diagram, you can also find a conclusion of Bayes' rule. What does Bayes' rule say? Okay, it says basically the probability of A given B, all right, is equal to the probability of B given A times the probability of A divided by the probability of B. This is the Bayes' rule. Okay. So basically it swaps the condition and the event, right? So why is that so? It could be easily read off the Venn diagram as well, right? So the probability of B given A times the probability of A, okay, is the joint probability of A and B, right? And the probability of A given B times the probability of B is also the joint probability of A and B, right? So since they are the same, okay, you can divide both sides by PB and got the Bayes rule. And you can divide both sides by PA, you got the Bayes rule on the right. Right, so this is the Bayesian theorem, which we will use. All right. So how many things did I review for multiple events? I reviewed joint probability, right? I reviewed conditional probability. And I reviewed a Bayes rule between two conditional probabilities. I reviewed three things. One last thing I will review with you is marginal probability. What is a marginal probability? So if you know the joint probability, okay, of multiple random variables, then the probability of one random variable among them is called a marginal probability. Okay, say if you know the joint probability of A and B, you want to know the probability of A, it's called a marginal probability. Okay, or if you know the joint probability of A, B, and C, three random events, and you want to know the probability of A, it's also a marginal probability. Well, you could also have the probability of A and B, which is a subset of A, B, and C. It's also a marginal probability. All right? So how do you calculate the marginal probability if you know a joint probability? Okay. If you know the joint probability of every possible outcome or every possible value of a random variable, then you can calculate the marginal probability by summing up the combinations. Say, I gave two examples here, right? So if you want to calculate the probability of A given the joint probabilities of A and B, then what do? You only need to sum up all possible values of B, okay? The joint probability with that B value, you get the probability of A. Okay, so let's say I have a joint event of tossing a coin and casting a dice, right? The coin could be up or down. The dice could be 1, 2, 3, 4, 5. Then I sum up coin up, dice 5, and coin down, dice 5 probabilities. I get dice 5 probabilities, right? So this is quite intuitive, right? Later I'll show you a table. So this is also referred to as I marginalize out the coin to get the marginal probability of the dice. Okay? So similarly, if you have 3 random variables, right? And you want to find the marginal probability of 1 random variable, and then what you do? You just sum up all possible values of the other 2, okay? And then get the total joint probability is the marginal probability of A. Maybe this figure is more intuitive. Let's say I have a coin and I have a dice. The coin could be head or tail. The dice could be 1, 2, 3, 4, 5, and 6, right? And you know, because this is a joint event, it has 2 times 6, 12 possible outcomes, right? 12 possible values of this combination. And you know, I distribute the probability mass of 1 into these 12 slots, okay? And it's like this. This is a joint event, okay? Coin up and dice 1. Coin up and dice 2. Okay, these are the probabilities. Then I say, or these are the numbers out of 1,000 experiments, right? Out of probability. Then I say, I want to get the probability of dice being 1. What do? I just sum up these 2 cells, okay? Along this column, I get the probability, marginal probability, right? So what if I want to get the marginal probability of the coin facing up? Then I just sum up all the probabilities in this row, right? Okay, no matter what the dice is, right? I sum up 1, up 2, up 3, up 4, up 5, up 6, right? I just sum up this row and I get the marginal probability of a coin facing up. Okay, this is called marginalization. All right, so in this spirit, if I want to get the probability of head, then I just sum up the first row, okay, and I get it's 0.43, okay. So this is called marginalization. All right, this is the last thing I want to review with you. All right, so that's a recap of week 2, okay. So in week 2, we learned the correlation between the data and model, and we look at what the data are like, right? And we looked at a modeling paradigm. So after we describe data curation, we end up having a flash through the probability theory. I'm assuming that everyone have learned probability, okay? And indeed, every one of you has learned it. All right, so that's about week 2. Let's switch to week 3. Okay, so this is the content for this week. This is the first week, actually. We roll up our sleeves and build a model. Okay, so the theme of this week is called counting relative frequencies. It's maybe one of the simplest models you see in this term, okay? So we will have 3 topics. First, I will describe maximum likelihood estimation as a training concept. In fact, nowadays, all the large language models can be seen as being trained using maximum likelihood estimation. Okay? And then the second part, we will build some language models. Okay? But not large language models, but rather small language models. Very simple language models. But you get a flavor of what they are. Third part, we will use the same principles to build a text classifier. Okay? You could also play with text classification. All right, so let's begin. we're building models. So we have to recap, what is a model? So last week we saw the correlation between model and data, but we didn't formally describe a model. Okay, so if you check the concept, a model is something, okay, with conceptual simplifications that makes mathematical calculation feasible. That's a model. Or, in other words, a model is something that simplifies the world, okay, and to make the computation feasible. You've also learned physics, right, in your grade 1, right? So when you describe some like throwing a stone off the cliff, right? You make simplifications. You forget about the shape of the stone, right? The air friction, etc. You only treat the stone as a mass point. Okay, that's modeling. Simplify things. Then you can calculate how fast it falls. All right. So throughout this term, we'll build mathematical models in the same spirit. Okay, we'll be simplifying things to make computation feasible. And of course, this week we are learning probability models. Okay, what is a probability model? We had a hint last week. A probability model calculates the probability of a modeling target, right? So whatever we model. For example, if I model language, the modeling target is language. If I model a parse tree, the modeling target is parse tree. Okay, and the probability model calculates the probability of this thing. Okay. But before we move on to language modeling, I still want to start with a very simple distribution, the Bernoulli distribution. Okay, so let's look at tossing a coin. Tossing a coin is a random variable. It has two values, head and tail. So the modeling target is the probability of the values. Okay, the probability of head and the probability of tail. All right. Let's also recall next week, after we have the modeling target, okay, what's the next step? The next step is we want to describe a function, right, to calculate the scores, okay, to calculate these probabilities. So, and this process is called parameterization. We need to build a model to calculate it. So, before we look at how we model it, we first look at how we do it. How do you model the probability of a coin? Okay, actually, we did something without thinking, right? Just as I just described. So, if you have a coin, you want to know the probability of facing up, right? Then you just toss it 1,000 times, 100 times, and you just count the number of times it ends up facing up, right? So if it's 53 times out of 100, then you say, my coin facing up is 0.53. You do this, right? So this is called relative frequencies. So in other words, you model a coin by counting relative frequencies. You know, that's the intuition. Or if you do it more mathematically, you say if you toss it n times, and k times it faces up, you say the probability of the coin facing up will be k over n. That's what you do. And when you do this, you actually build a model. You already parameterize the model, and you already train the model from data. Okay, let's look at how you parameterize the model. In your mind, you actually have one model parameter. Okay, let's write it down as theta. Okay, you model this whole thing by calculating the probability using one model parameter called theta. And the way you calculate the probability of model of the coin facing up is the probability of head is theta. Then how do you calculate the coin facing down? Is the p of tail is 1 minus theta, because it's a probability distribution, right? So that's a very simple equation, and you already built this model. This process is called parameterization. What do I mean? I mean you define some model parameters to specify a scoring function to calculate your target probabilities. Okay? That's intuition, but this is the mathematical description. And then how did you train the model? What's training? As we looked at the thing last week, right? If you train a model, you need some data. So the data is your experiments, right? You toss it n times, and you end up with k times head. So that's your data. Okay, and using this data, how do you train the model? By training the model, I mean I decide the value of model parameters. Okay? So, okay, how do I decide the value of model parameter? I say k times out of n, so that's the value of my theta. That's the training process. Okay? All right. So, we built a model and we trained the model. So, although it is intuitive, you actually did 3 steps. First, you decide the modeling target. Okay? Second, you does parameterization. You describe the scoring function, how to calculate it. And you found one model parameter theta. And third, you sort of you got a set of data and you specify the value of theta. Okay? So this is called model training. You distill knowledge from data into model parameters, theta, and you finish training. These 3 steps. That's easy to understand, but there's no theory. I only described 3 things for you. Is there any theory? Why do I train the model this way? Okay, there's a very simple principle called maximum likelihood estimation, or MLE. That's the theory behind counting relative frequencies. Okay, so what is maximum likelihood estimation? Formally, you have a set of training data, okay? I describe the training data as y1, y2 until yn, the n experiments, where each y describes the value of a random variable, whether heads up or down, okay? Head or tail, head or tail, all right? So, the principle of maximum likelihood estimation is, okay, to maximize the probability of your training data according to the model. Okay, there are 2 things you need to be aware of. The first is, how do you calculate the probability of your training data, right? How do you calculate the probability of your training data? You toss the coin n times, and k times it faces up. What is this thing? This is a binomial distribution, isn't it? Right? It's n experiments. So, the probability of your data is a binomial distribution, or n Bernoulli experiments. Okay? But there is something. They are independently and identically distributed. What do I mean? I mean, the n experiments are conditionally independent of each other. Okay? And every time the Bernoulli experiment has the same distribution. Okay? So this is called IID. So only when your experiments are IID, you have the binomial distribution. Okay? I need to describe the probability of my data sets using my model probability. In other words, I need to describe the probability of this y, okay, using my model parameters. They are theta and 1 minus theta, right? So head or tail. So this is the first step. I describe the probability of my data using my model parameters. The second step. Okay, this probability of the data is called the likelihood. Okay? We call it likelihood. You want to ask me why? Let's just take my word for it. Okay? If you're interested in learning more, you can look at Bayesian learning in chapter 13, but we won't describe it in the lectures. Okay? But let's just say it's called likelihood. You describe the data likelihood using your model parameters, and then what do you do in the next step? In the next step, you want to find the set of model parameters that maximizes this likelihood function. It's an optimization problem. Okay? You want to find the value of your theta that makes your data the most likely. Maximum likelihood training. Okay? Training is to find your model parameter value from your data. And maximum likelihood estimation is to maximize the likelihood of your data to find the parameter. Okay? So let's look at what is your data likelihood now. It's a binomial distribution, right? For this particular set of experiments, you know, the order is already determined. So you forget about that coefficient, and you know this is theta to the power of k times 1 minus theta to the power of n minus k. Easy to understand, right? First time it's a head, right? Theta. Next time it's a tail times 1 minus theta, right? Third time it's a head, then times theta. And in the end, how many times did you multiply theta? K times, right? So that's the equation. That's a description of your data likelihood using your model, okay? And then all you need to do is to find the maximum value of that equation, right? To change theta to find the maximum value, and then you got the value of your theta, right? So that needs a little bit of calculus knowledge, right? How do you maximize that thing? You want to find its derivative with respect to theta, right? This thing can go up and then go down, you know. Then you want to find the point where it plateaus, right? So how do you do it? You take the derivative of this thing with respect to theta, okay? And everyone knows how to do it. And here I just quickly show you the equation. Directly optimizing this thing can be more challenging, but optimizing the logarithm of this thing is easier. So I maximize the log likelihood of my data. I can do this, right? So I maximize the logarithm of theta to the power of k times 1 minus theta to the power of n minus k, right? Some of you is doing the calculation offline, I guess. But if you look at it, you use the derivative chain rule, right? And you solve the equation, you'll find the analytical solution. The theta that maximizes your likelihood is k over n. Okay? Now, if you're quick enough, you already solved the equation. If you're not quick enough, I leave it to you to do it offline. Okay? Who want me to do it on the blackboard? Okay, none of you want me to do it, and you are smiling, so I guess most of you can do it. It's very simple, right? So, yeah, you're nodding. So the derivative of a logarithm is 1 over something, right? And then you use the chain rule. You can quickly find that in the end, it's like k divided by theta minus n minus k divided by 1 minus theta is equal to 0. And when it plateaus, and you solve this equation, you get the result. I leave it to you to do it offline, okay? All right. So, I'm trying to explain to you, right, what happens when you do this relative frequency counting, okay? You just toss it 100 times, and 53 times it faces up. You say the probability of it facing up is 53. But you did 3 things. Let me just recap the 3 things, okay? First, you found the modeling target, which is the probability of facing up, right? That's what you calculate. Second, you parameterized the model, right? You found an equation, how to calculate the probability. And in this equation, there are some model parameters. One called theta, right? Third, you train your model. By training your model, you distill knowledge from your data into your theta, and you end up with theta, and that's it. You forget about your training data. And this process is maximum likelihood estimation. The idea behind it is that you obtain some data set, okay? This data set must mean something, right? Okay, you assume that the data set you get is the most probable result you get in the universe. Okay, and then you train your model according to it. That's called maximum likelihood estimation. Is there some deeper theory, more theory behind maximum likelihood estimation? We will learn that in week 7 when we learn entropy, etc. Okay, you'll have a new view of maximum likelihood. But now let's move a little bit closer to language models. Okay. I just hinted to you that a language model, drawing a word randomly is a categorical distribution, right? So it's no longer a Bernoulli distribution. So you would draw, it's reminiscent to casting a dice. So let's just recap casting a dice. The modeling target is the number you get, 1 to 6, okay? And how can you parameterize the model? The way I parameterize the model is, again, I use a separate model parameter to describe the probability of every outcome. Okay? So the probability of 1 is one parameter, theta 1. The probability of 2 is one parameter, theta 2. The probability of 6 is theta 6. Okay? But out of these 6 parameters, only 5 of them are free. The 6th one depends on the 5 because they add up to 1. Right? So there's a constraint. Because of this constraint, you only have 5 free parameters. And this parameterization trick is what we do throughout this week. Okay? So whatever the random variable values are, I just treat the value probability as a model parameter. This is what we do. So when we have these model parameters, and we have a set of experiments, I cast the dice 100 times and count the numbers of 1 and 6, right? I end up with a model training algorithm that derives every theta by the corresponding relative frequency. If out of 100 times I see the number 1 20 times, then theta 1 will be 20 over 100, counting relative frequency. Okay. It can be proved that maximizing data likelihood leads to relative frequency estimation. This is a homework exercise. Okay? You do it, you get scores. Okay? You just take the partial derivative with every theta, right? You maximize the data likelihood, you get the theta values. Okay, it's an exercise. All right. So maximum likelihood estimation leads to counting relative frequencies. Then, now, let's talk about drawing a word. Now I'm saying, you want to randomly draw a word, okay, from the vocabulary. Okay? Again, a vocabulary is a set of words you know, or a set of words that the model knows. It's called a vocabulary. I normally describe it as V, okay? And V norm is the number of words in V. All right? So it's like casting a casino dice. It's only that numbers are much more than 6, right? So how many words you have in the vocabulary, then how many faces the dice has. So the modeling process will be exactly the same. The modeling target is probability of a word, PW, okay? And how do you parameterize the model? You just take a separate model parameter, okay, to represent the probability of each word, okay? The probability of the is 1 theta. The probability of cat is 1 theta, etc. So you have V norm parameters. All right? So this is how you calculate those probabilities. And how do you train a model? Now you need to find a set of linguistic data. So you collect a set of news or you collect a set of books, no matter what. And we learned last week, this is called a corpus, right? And we have already learned that for categorical distribution, maximum likelihood estimation leads to relative frequency counting. Then you can train the probability of every word by counting how many times the word occurs in your corpus, okay? Divided by the total number of words in your corpus. Now the total number of times every word occurs, right, in a corpus, or the size of the corpus in the number of words. So this is relative frequency counting. If your corpus has 1 million words, okay, and 53 times you see the word model, then the probability is 53 out of 1 million. Okay? So that's word drawing. All right. Before I finish this class, let's just recap 3 steps. You end up with a model, okay? First step, decide the modeling target. I want to model the probability of something. What is that something? Okay? Second step, parameterize your model. Find an equation to calculate these probabilities. In the equation, there must be some parameters. Third step, fill the model parameters, okay, by training over a set of data. And for this week, we'll just do the relative frequency counting, MLE, right? So now we move on to n-gram language models. So what are n-grams? What is a language model, first of all? A language model, as it says, models languages. Okay, it can be used to analyze or generate natural language sentences. So this is called a language model. In natural language processing, most of the language models are probabilistic language models. And these language models, they calculate the probability of sentences. Okay. Maybe a language model can calculate the probability of words. All right. You know that thanks is more probable than hyperbole or Markov. Okay, this is like the word drawing game. Other language models can calculate the probability of sentences. Okay, say he said hi is probably more likely than said he hi. Okay, so the first thing you know that language models calculate the probability of sentences. So how do you calculate the probability of sentences? Now for today, we discuss n-gram language models. Okay, so these language models, you know, they parameterize the model by calculating sentence probabilities using n-gram probabilities. All right. So what is an n-gram? So n-gram is n consecutive words. Okay, this n describes the number of consecutive words. When n is 1, n-gram language model is called the unigram language model. So unigrams are just words, hello or Markov, etc. So when n is 2, okay, you get bigrams. Eat pizza is a bigram. Jump up is a bigram. So similarly, when n is 3, you have a trigram. Okay, I like NLP is a trigram. Okay, or like NLP period is also a trigram. It doesn't have to make sense as long as it's 3 consecutive words. Okay. Well, you can have 4 grams, 5 grams, 6 grams, 7 grams, or n grams. Okay. So n-gram language models, the modeling target is the probability of a sentence. How do you calculate the probability of sentence? They use n-gram probabilities to calculate the probability of sentences. Okay, that's n-gram language model. So let's look at unigram language model. The modeling target is the probability of a sentence denoted as S, PS. How do you parameterize the model? Okay, I model the sentence as a set of unigrams. Or I model the sentence as a bag of words. I assume that every word in the sentence is IID. All right? Then it's like I generate a sentence by randomly generating a word, and then randomly generating a second word, and then randomly generating a third word. Okay? This is too much simplification, right? You know the words are correlated. But remember, modeling is to simplify things, to make computation feasible. All right? So the simplest thing we can think of when calculating the probability of a sentence is like this. Okay? So, and then this can't be more familiar. So this is a set of categorical experiments, right? So it's a multinomial distribution. Okay? Or if you care about the order, it's just a multinomial distribution without the coefficient. So the probability of a sentence is the probability of a first word times the probability of a second word, blah, 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 times the probability of the last word. Or it's the product of every word probability. And that's a unigram language model. Okay? So I ask you, how many parameter types do we have? How many types of parameters? Okay, we only have one type of parameter, the word probability, right? So how many parameter instances do I have? So how many independent parameters are there in my model? Because every word probability is a separate parameter, right? So the number of parameters is the vocabulary size. All right. Now, how do we train the model? Because every model parameter is a separate word probability, we can train the model by using maximum likelihood estimation. In other words, it's the same as the word drawing model, right? So I just need a corpus. The probability of every word is the relative frequency of this word in the corpus. The more times it occurs, the more likely it is. Very simple. All right. So although it doesn't consider the word order, it can already tell you some differences. For example, if I say hi, this is a very likely sentence, right? But if I meet you, I say hyperbole, it's a very unlikely sentence, right? So you can already differentiate sentences. But there's one thing, before I move on to bigram language models, the thing is, there could be out-of-vocabulary words. What do I mean by out-of-vocabulary words? If you want to use the model to analyze sentences, right, to calculate the probability of sentences, then you know the model must have a vocabulary, or the model must know a set of words, right? Just like you and me, right? I know a set of English words and a set of Chinese words. Where does the vocabulary come from? It comes from your training data, right? So whatever word the training data has, the word the model knows. If it's not in the training data, the model doesn't know. Then when you try to analyze some test data, you could have an issue of out-of-vocabulary words. Say, if your training data doesn't know hyperbole, okay? And if your training data doesn't know Markov, okay, there's a model in NLP called hidden Markov model. So that's why I always say Markov. Then you have an issue. Because, say, I invited Markov to dinner, or I invited hyperbole to dinner. These are two sentences, right? But you can't tell the difference. Why? Because according to maximum likelihood estimation, the probability of both Markov and the hyperbole are zeros. They did not occur in your training set. Then whenever a sentence has an out-of-vocabulary word, you cannot calculate the probability of the sentence. We want to avoid that issue. This is called out-of-vocabulary issue. Okay? Now how do you do it? How do you do it? All right. In order not to let out-of-vocabulary words affect your estimation of the other words. Okay, I should use a better example. Let me rephrase my example. Say, if I have a unknown word called Markov, okay? I say one sentence, I invited Markov to dinner. This is one sentence, right? The other sentence is, I hyperbole Markov jump easy, okay? That's two sentences. Of course, you know the first sentence is more likely, but both sentences have probability of zeros, right? You don't want like out of vocabulary word Markov to affect the calculation of the other words' probabilities. All right. So to solve this problem, I need to be able to calculate the probability of out of vocabulary word. All right. So how do I do it? Let me introduce a special token called bracket OOV bracket. Okay. So this is a new word, just called, this is a placeholder token in my vocabulary, okay? And that token represents every unknown word, all right? Then your vocabulary becomes your old vocabulary plus one, right? This one is OOV, the first thing. Now the second thing, okay, in your original model, this OOV will be zero probability, right? You don't want to do that, right? You want to give it a small probability. Then, how do I do it? Okay, I can just say the unknown word has a probability of epsilon. Okay, but that's too ad hoc. Is there a more principled way of doing it? It turns out that the more principled way is called add-one smoothing. Add-one smoothing. The idea is, you calculate the probability of every word by counting relative frequency, right? Okay, now you got the count of every word. And you have an OOV word, which has a count 0. Let's do this. Let's add 1 to the count of every one. Okay? So originally some word occurs once. Now I assume it occurs twice. Some other words occurs 1,000,000 times. You assume that it counts 1,000,000 plus 1 times. Okay? And for those who occur 0 times, you assume that it occurs once. Okay, add 1 to every count. And then you can recalculate the relative frequency in this equation. Okay? This is called add-one smoothing. So your OOV will be 1 divided by the total number of words plus V. Right? Because every word increases 1. Okay? This is called add-one smoothing. By using add-one smoothing, your out-of-vocabulary words have a non-zero probability, and you can distinguish I invited Markov to dinner and I hyperbole Markov easy up, right? Something like that. Why do you add 1? You could add a different number. Let's say the number is called alpha, okay? And then you can extend, generalize your add-one smoothing to add alpha smoothing. Alpha could be 10, could be 0.1, whatever, okay? You can adjust the alpha value to optimize your model performance. So alpha is called a hyperparameter. It's not a model parameter because I said model parameters are parameters that are introduced into the score calculation, right? Alpha is not one there. It's not trained from my data. But alpha is sort of tweaked by myself. I can say alpha is 1, I can say alpha is 10, right? So this is called a hyperparameter. It's not a parameter. It's sort of a meta thing, right? I can determine before I build the model, and I can compare the performances with different alpha values. This is called a hyperparameter. But where can I tune the alpha values? Shall I try different alpha values and compare the model on my test data? I said no last week, right? Because you do this, your model fit too well on your test data. You don't know how it generalized to new data. So you need a validation set or development set to tweak alpha. So hyperparameters must be tuned on your development data. Remember, 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 okay? But why do you say add alpha smoothing is more theoretically justified compared to just having P of OOV equals to epsilon? If you're interested, okay, chapter 12 of the first edition will have it, okay? You can read the textbook. Then in this term, we will not discuss it, okay? But I show you a figure. So this is the probability distribution, okay, before smoothing. And this is the probability distribution after add 10 smoothing, okay, over a set of data. You see what? The difference between the probabilities are smaller, right? This is more sharp. This is more smooth. That's why it's called smoothing. Okay? In other words, I take probabilities from the rich words and distribute them to the poor words so that it's like more balanced, more smooth. Okay, in your lab, if you don't do smoothing, if you don't have OOV, your model will perform worse than other people's model. Now let's play with bigrams. You know that unigram language models can differentiate some sentences, but it cannot differentiate between he ate pizza and he drank pizza. The reason is that both eat and drink have similar probabilities. I don't know whether eat will occur more frequently or drink will occur more frequently. Okay? But the combination of eat and pizza and drink and pizza differs. You don't see many times someone says drink pizza, right? But you see a lot of times people say eat pizza. All right. So I can model the probability of bigram by using conditional probability. Given that the previous word is eat, what is the probability of pizza? Given that the probability of drink, what is the probability of pizza? So this is called a conditional probability, okay? You can calculate the conditional probability in relative frequencies. Just recap what we have reviewed earlier. This is the Venn diagram. You count the relative frequency of A, okay, within B by using this shaded area to divide the area of B. So that's the probability of A conditioned on B, right? When I translate this intuition into equation, I get this. The probability of a word W2 given W1 is the number of times the bigram W1, W2 exists in your data set divided by the number of times you see W1 in the data set. Okay? Or the number of W1, W2 divided by the number of every possible W, W1, W added together. Right? So that's the probability of W. That's the count of W1. All right. So this equation corresponds to this Venn diagram. So you count W2 provided that the previous word is W1. Okay. There's something to consider for these conditional probabilities. The first is called sparsity. Okay, maybe I will use the word sparse later in this course also. And maybe you will see the word sparse when you read the literature. What does sparse mean? Sparse means that out of a set of things, okay, a set of counts, if many are zeros, this set of counts is sparse. Okay? If none are zeros, it's dense. Okay? All right. And then I claim that bigrams are more sparse than unigrams. Why? Think about it. The number of possible bigrams is V times V, right? V times V. But the number of bigrams you see in a corpus is roughly the same as the number of unigrams you see in a corpus, right? If you scan through the corpus, 2 words by 2 words, right? It's almost the same as if you scan through the corpus 1 word by 1 word, okay? So the count of non-zero is almost the same. But you divide this count, one by V, the other by V times V. So for sure, there are many possible bigrams you will not see in your corpus. So bigrams are more sparse. So if the sparsity is more, you know, the OOV bigrams will be more, right? So you need some more advanced techniques to avoid OOV. Here is one called interpolation. What is interpolation? So you use a weighted sum of bigram probabilities and unigram probabilities to represent interpolated bigram probability, as I write here. So the bigram probabilities are counted in whatever I show it in your last slide, right? And the unigram probabilities are just calculated by the words without the condition. And then I have a hyperparameter lambda. I say the interpolated version is lambda times the naive version plus 1 minus lambda times the unigram probability. Okay? So the bigger the lambda value, the more I trust the bigram probability. The smaller it is, the more I trust the unigram probability. Okay? So it's a hyperparameter. You tune it over validation set. In this way, if your unigram probability is smoothed, okay, and your bigram probabilities are counted, then you will always have non-zero values in your bigram probabilities. This is called interpolation. All right. Now that I know how to train bigram probabilities, let's look at our whole model. As I mentioned earlier, the modeling target, okay, is the probability of a sentence. And this time, because I'm counting bigrams, I want to add a special symbol S to the beginning of the sentence, and a special symbol /S to the back of my sentence, just to mark the two ends, okay? With this S and /S, my equation will be simple, okay? The probability of sentence is equal to the product of all the bigram probabilities in it, as I show you in this equation. Okay, so in this equation, I parameterize the model using bigram probabilities. So that's a bigram language model. I only have one parameter type, okay? And I have a lot of parameters. Depends on how many bigrams I know, right? Okay, that's symmetric to my unigram language model, you know. You just multiply all the bigram probability together. And you might ask me, is that true? Right? Why do you do that? For unigrams, I take IID assumption, right? For bigrams, there's no theory. I just multiply all the bigram probabilities together. Something's missing, right? When I read it, I don't feel safe, right? Unless I can prove it. How did I parameterize my model? I want to derive it. Actually, there is a derivation. But the derivation uses something called the probability chain rule. The chain rule looks like this. The probability of the sentence is the probability of the first word given S times the probability of the second word given S and W1 time until the probability of a slash S given S until Wn. Okay, so this is called the chain rule. Why is that so? I guess you all learned the probability of chain rule, but let me just prove it for your memory, okay? Let's say I have a joint probability P, A, B, and C, okay? I want to use the probability for every something, okay, to represent this thing. Then what do I do? All right, first time, it's equal to PA times P, no, sorry. PA given B and C times P, B and C. That's okay, right? Let's write it the other way, the more similar to the n-gram language models. All right, P, A times P, B and C given A, okay? You all know that this is true, right? Because this is just a conditional probability. You take B and C as one event, okay? And that's just conditional probability, right? PA and BC is equal to PA times BC given A, right? I just reviewed it, right? So this is conditional probability. All right, and then I can further derive it. PA times P, okay, B given A times P, C given A and B. Why is this true? Okay, you only need to look at this part now. So B and C is a joint event, conditioned on A, all right? So you will have A on the condition of everything. Now then the same thing will happen. So B and C is a joint event, so the joint probability is equal to the B probability times the C given B probability. Again, this is the conditional probability, right? It's just that we put A on the condition. All right, so you can do this continually, right? Continuously. So you take one variable out, the second variable out, the third variable out, okay? And then you end up with something like this. So this is called the probability chain rule. Okay, so great. I know that the first step is right. But again, it's not my bigram model. The second step is a little bit approximation. So I'm saying that using the chain rule, you know, the condition is more and more, right? So I want to simplify things. Let's make a conditional independence assumption. Again, this is modeling. Modeling simplifies things, okay, to make computation possible. I am simplifying the thing a little bit to say every word is conditionally dependent only on its previous word. All right, in other words, I just cut everything else, right? I just cut everything else. I just leave the previous word in the condition. This is called conditional independence. as discussed. So after the chain rule and after I make independence assumptions, I get this equation, right? So that's the multiplication of every background probability together. All right, so what did you learn? You learned the trick to parameterize your model. When you have a joint event, okay, you can apply the chain rule and independence assumptions to model it. All right. All right, so now let's use the same trick to derive the trigram language model. The modeling target is the probability of a sentence, okay? How do you parameterize the model? You do it by first applying the chain rule, and then you make independence assumptions, assuming that every word is continually dependent on only the previous two words, all right? And you end up with this equation to calculate the probability. It's the multiplication of all trigrams in a sentence. But you have to assume that two as symbols are in the beginning. And they must happen. The probability of them are ones. Okay. So for trigram language models, you have one parameter type, trigram probability. How can you train it? Just by counting relative frequencies. How many parameter instances do you have? How many trigrams do you have in your corpus? How many instances you have? Okay? So that's trigram language models. So this is the training equation. You count the particular trigram you try to estimate divided by the count of the bigram in the beginning. Okay. Of course, trigrams are also very sparse, more sparse than bigrams. So you can use interpolation. So interpolated version of trigram probability is lambda 1 times the original one plus lambda 2 times the bigram 1 plus lambda 3 times the unigram 1, right? So if you make sure that the three hyperparameters add up to 1, you ensure that all the probability of all W's add up to 1. You can prove it, right? Because each term will add up to 1 themselves. In the textbook, there are more different methods that deal with sparsity. One is called Nasser-Nye smoothing. One is called the good Turing smoothing. One is called back-off. They are all very interesting. So if you're interested, you can read the textbook. If you're not interested, you're fine, right? Because you have more exercises than necessary to get A. There's one thing I need to remind you, which is, when you have trigrams, those probabilities can be small. And when you calculate the probability of a long sentence, you need to multiply them together. It can be numerical underflow. All of you know it, right? Because you learned computer science. The absolute value becomes too small, right? So your computer cannot hold it, right? So it becomes 0. So to avoid this issue, you can again take the logarithm. The product of these probabilities is the sum of their log versions. Okay. So use log rather than the original probabilities. Okay. Now that you have a language model, you can measure the probability of sentences. You can also generate sentences using a language model, right? When you ask large language model, DeepSeek, tell me how to do this homework. Don't do it, okay? So it generates a sentence to answer your question. How do you generate? Okay, we could also generate a sentence using our n-gram language models. We do it by sampling words from the beginning of the sentence to the end, okay, according to our probability. So I first generate W1, okay, by sampling W1 according to the n-gram probability. Then I want to generate W2 given W1, right? Then I generate W3 given W1 and W2. And then I generate W4 given W1, W2, and W3. Now if you make an independence assumption, W4 might depend on W3 or W2 and W3 or nothing, okay? But whatsoever, you generate word after word from left to right. When you generate each word, okay, you only know its probability. How do you turn this probability into a word? Okay. You can do the thing as I write here, okay? You know the probability of all vocabulary words, they add up to 1, right? So you can put all the words into a horizontal bar. The probability of W1 is here, the next word here, the next word here. You arrange them together, and you know the relative size of the span corresponds to its probability. But they must add up to 1, right? And then what you can do is you draw a random number from 0 to 1, okay? It's like 0 or 1 or 0 or 1, stop. Random number is here, right? The random number falls into a span of your words. Wherever it falls, you draw that word out, right? Of course, if some word is very probable, then you know the more chance you draw this word. Okay? So this is called sampling. You can do random sampling. All right. And to tell you the difference between unigram, bigram, and trigram language models, we did sampling. We trained those language models using Shakespeare plays. And then we sampled sentences. So when you use unigram language models, I think the sentences doesn't make sense, right? You read it yourself. But if you use a bigram language model to generate sentences, they start to make a little bit sense to me. Okay? You read it yourself. But if you use a trigram language model, I think they read like Shakespeare. Where is the lady of the house of York? Okay, I think they look like Shakespeare. Okay? To the level of my English literature fluency. All right. Okay, so you can do more like you can build a 4-gram language model, 5-gram language model. But you know, when you go to 6, the model will be very sparse. And there are too many n-grams there, so the model will also be very slow. You can't do it. So it means this simple parameterization trick has a limitation, right? Later, you know, in week 9, when we move on to neural language models, we can solve the problem. We can model infinitely long history by using different way to calculate the probabilities. But let me tell you a concept called generative models. Generative models are models that calculate the probability of joint events by generating the sub-events one after another. So n-gram language models are definitely generative models because they calculate the probability of sentences by generating one word after another, right? So it uses a generation process to calculate the probability of a joint event. That's called a generative model, all right? By the use of probability chain rule, I calculate the joint probability by generating one word after another, okay? So in these pictures, so every circle represents a sub-event, and the links show the conditional dependencies. Okay? By using the chain rule, the figure is complex. But I can cut the figure by assuming, by making independence assumptions. So this is a bigram language model. Every word depends on only previous word. So this is a trigram language model. Every word depends on the previous words. So this kind of independence assumptions, where a sequence things, in a sequence of things, everything is dependent on only a fixed number of previous things. It's called Markov assumption. Oh, so that's where Markov comes out, right? All right. You will learn hidden Markov models later. But before we finish, I have to introduce you a text classifier called the naive-based text classifier. Okay? It's a generative model. The input is a document, the output is a class label, as I showed to you earlier, right? So this is text classification. Now, you can do the model. If you represent the document as D, the class label as C, then the model target is PC given D. Okay? Given my document, what is the probability of the class label? That's the modeling target. And say, all right, cool. Let's just take the probability of every C given D as a separate model parameter. I can do it, right? Given one document, whether it's a class 1, class 2, I use separate parameters to do it, to represent these probabilities. But then this model will have a serious issue. Why? Because if you train it by counting relative frequencies, you know, every parameter is like the count of D and C divided by the count of D, right? So this is like relative frequency. But why is there an issue? Because the document is very sparse, right? So in your training data, probably every document occurs only once, right? You won't assume that the document occurs 10 times, and 9 times is labeled positive, 1 time is labeled negative. It's impossible. Every document occurs only once, and it only occurs with a fixed class label, all right? So, given a document, the class label in the training data has a probability of 1, right? The class label that does not occur in the training data has a probability of 0. Okay? It recites the training data. And then in your test data, there's a new document, not in your training data. OOV, right? So D is not seen. There's no count D and C. So every test document and every class label is out of vocabulary. You cannot compute. So this simple model, this simple parameterization fails. It only recites your training data. No generalization power. Too sparse. I need to be able to compute, you know, the probabilities of unseen documents. How do you do it? You say, I know. You just told me it's chain rule plus independence assumptions, right? I just break the joint events into sub-events and I make independence assumptions. I can do it. Can you do it? And then there's another issue. It's not a joint event. C is a single event. Like I can't just break C into. The problem comes with D, not C, right? But D is the condition. How can I solve the problem? Can someone tell me how to solve the problem? We just reviewed Bayes' rule, right? It swaps the condition and the event. So PAB is PBA times PA given divided by PB, right? So let's, if we apply Bayes' rule to the problem, then I will see PC given D is equal to PD given C times PC divided by PD, as you see in this equation. Now that's great. So D comes to the event, right? So and then further, right? Given that your test input is D, so PD doesn't matter, right? You only want to compare different C given this D. So PC given D is proportional to PD given C times PC. What is that? That's the joint probability of C and D, right? So I'm trying to say that by using Bayes' rule, I swapped PC given D into PD given C times PC. Okay. And then you can make chain rule and independence assumptions. In particular, you can break PD given C into the product of every word in D, PW given C. What is this like? It's a unigram language model, right? Conditioned on C. A unigram language model is a bag of word model. This RID assumption is called a naive assumption. Very simple, very naive. Okay? So, because I used the Bayes rule, I made a naive assumption. This model is called a naive Bayes model. All right? And then in the end, you will have the final form of the model. The modeling target is PC given D, and your parameterization is the product of every W, PW given C times PC. Okay, so this is how to calculate scores. You have two parameter types. One is PW given C, one is PC, right? So you have how many parameter instances? It's the vocabulary size times the number of class labels, roughly. And how do you train the model parameters? So for PC, you just count, okay? You have a set of documents. Each is assigned a class label. So DC pairs are your training data. So you need to label your corpus, right? Okay, so out of the corpus, if a proportion is positive, then you take the relative frequency, that's the class probability. Then how do you calculate PW given C? Then you count the relative frequency of W only in positive documents, right? So it's a relative frequency. So that's how you train your naive Bayes model. I don't know if I'm too fast, but if I am, please read the slides and the textbook for doing it, for reviewing it. Okay? So, so this is how you train your model. But of course, to avoid numerical underflow, you have to use the logarithm of the probabilities. Okay? As I mentioned to you, for testing, you're given a document, you're supposed to calculate class probabilities. You just use your parameterized model, train the model, to calculate the probability of every class label given the document. Okay? And then you choose the most probable class label as the output. All right. So this is the generative story of naive Bayes model. Our modeling target is the probability of the class given the document. Okay? Our parameterization is to calculate the joint probability of the document and the class label. So this is my parameterization again, right? So PW given C multiplied together times PC is my equation to calculate the joint probability. I can draw this equation here. Okay, I sample a document and a class label by first sampling the class label. I want to generate a positive document. Okay, and then I generate a bag of words independently given this class label. Okay, this picture can be simplified into this picture. This is called nested plate notation. So given the class label, I draw n words. N is the size of the document. Okay? All right. Because we ran out of time, I stop here and I make a summary of today. So for this week, we learned a very simple form of the model. Okay? Probability model. These models, okay, are parameterized by using Bayes rule, chain rule, and independence assumptions. I turn a target probability into smaller probabilities, basically this parameterization. And I train the model by counting relative frequencies. Okay, every model parameter count relative frequencies. And you're ready to build any model in this way. And we learned two types of such models. One is a language model called n-gram language model. One I just introduced very briefly You can review it yourself. It's called naive Bayes model. All right? And they are all generative models, which simplifies a joint probability into a process to generate every event in it. All right? So that's it. So next week, we will move on to discriminative models, which are different from generative models. I see you next week.